Greetings, it's Paul Bamberg welcoming you to the preview video for Class 2 in Math S-322. I'm expecting that everyone will watch this before Tuesday morning, so you'll have an idea of what we're going to be doing in class the next day and how the various proofs and examples fit in. The subject is sequences and their limits. Let me start by introducing a bit of notation. These quantifiers are absolutely standard in serious mathematics. For some strange reason, they're not used by Ross in our textbook, but they save a lot of space when you're writing on the board, and I'm going to encourage you to use them throughout the course. The first of these is called by logicians the existential quantifier. It's written like a backwards capital E. It's read there exists, and it's almost always followed by the phrase such that, which in that context you can feel free to abbreviate as S period T period. Here's an example of its use. The logical proposition is there exists an x such that x squared equals 4. That's a true statement. Why? Because either x equals 2 or x equals minus 2 has the property that its square is equal to 4. The other quantifier is the universal quantifier. It's an upside down capital A. You can read it for all, for each, or for every. And you use it to specify that some proposition is true for every member of some set or sequence. In most of the interesting cases, this set or sequence will be infinite. So here's an example. For all x in the real numbers, x squared is greater than or equal to 0. That's a true statement because whether you consider an arbitrary positive number, an arbitrary negative number, or 0, the square is either 0 or positive. Change it slightly to, for all x in the real numbers, x squared is greater than 0. Now that's a false statement. It's true for all positive numbers, it's true for all negative numbers, but it's not true for 0. One counterexample is enough to kill it. Which brings us to the next idea, how to negate these quantifiers. Let's start with a statement of the form, there exists an x such that p of x is true. For example, there exists a prime number such that that prime number is even. That's a true statement because 2 is a prime number. What would be the negation of that statement? The negation of that statement would be all prime numbers are odd. For all x, the proposition p of x, that the prime number is even, is a false statement. So, to negate the proposition, you do two things. You convert p of x is true into p of x is false, and you also replace there exists by for all. The same rule works if you're trying to negate a for all statement. If you start with for all x, p of x is true, how can you refute that statement? Well, you refute it by showing a counterexample, and you only need one example. There has to exist an x such that p of x is false. So, if I start with the statement, all prime numbers are odd, that is a false statement, and I want the negation of that statement. The negation is there exists a prime number such that p of x is not odd, it's even. And that's a true statement because 2 is an even prime number. Now we can get to sequences. A sequence is arguably really a function. The domain of the function is the natural numbers. You can start with 0 or 1 or even some larger integer m if it strikes your fancy. And the domain is all the little n's that are integers greater than or equal to your starting integer m. The codomain of the function in this course is also always going to be a real number, because we're doing a course in real analysis. In other branches of mathematics, you could have sequences of vectors, or sequences of complex numbers, or sequences of matrices, but we're just going to deal with sequences of real numbers. To denote a specific element in the sequence, we subscript S, the symbol for the sequence, with n. So S sub 2, for example, would be the second element of the sequence. If we want to denote the entire sequence, the long-winded way is S1, S2, dot, 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 which makes it very clear we've got an infinite sequence, or S sub n in parentheses for n in the natural numbers, or even S sub n enclosed in parentheses. It's important to use parentheses and not curly braces. If you use curly braces, you're denoting the set of values in the sequence, and it's possible to dream up a sequence for which, although the sequence is infinite, the set of values is only finite. Consider, for example, the sequence where the nth element in the sequence is the cosine of n times pi. Cosine of pi is -1, cosine of 2 pi is 1, cosine of 3 pi is -1, so the set of values in the sequence is just the two-element set consisting of -1 and +1. Parentheses to specify the sequence, curly brackets to specify the set of values in the sequence. Now I can talk about the limit of the sequence, and in most cases in this course where we work with limits, we're going to reduce the problem to limit of a sequence. For the limit of a sequence, the only limit you can consider is the limit as n becomes very large. And for that reason, it's unambiguous to write lim of s sub n instead of the more long-winded lim as n approaches infinity of s sub n. Now for the key definition. A sequence, s sub n, is said to converge to a limit s if, by making n large enough, you can get all the remaining values in the sequence to be as close as you like to the limit s. So let's consider how we write this formally. You start by specifying how close to the limit you want it to be. You say, I challenge you with epsilon equals 1/1000th. I have to respond to your challenge with a capital N, a counting number, and I choose that so that for all little n that are greater than that capital N, the nth element of the sequence differs from the limit s by less than epsilon. Notice this absolute value. It has to lie in the open interval from s minus epsilon to s plus epsilon. And this is almost always done with these symbols. Epsilon specifies how close you want to get. Capital N specifies how far along in the sequence you have to go. And little n specifies an arbitrary element of the sequence beyond the capital Nth element. It's a bit of a pain to prove that a sequence converges by using this definition, because in order to apply the definition, we have to know the limit s of a sequence. Once we can figure out that limit, the rest of the proof is purely algebra. The algebra turns out to be rather messy, and we will come up with better ways of doing this starting in the third class. You might worry that a sequence has more than one limit, but that can't happen with sequences of real numbers. If a sequence converges to S and that sequence converges to T, then S equals T. That seems so obvious you might think it would be hard to prove it, but in fact it turns out to be very easy to prove it, and it will be our first example of the use of the triangle inequality, which I introduced last time for doing real analysis proofs. Ross devotes several pages to the issue of formal proofs. A formal proof is one that includes the minimum number of statements required in order to establish the truth of some mathematical proposition, and frequently that involves throwing away a lot of the scratch work you did in order to figure out how to do the proof. You'll discover this when you try to construct these formal proofs on your own. You say, I need to prove that this particular sequence converges to 3. And you figure out by playing around that if someone challenges you with an epsilon and you choose a capital N that is an integer greater than 17 over epsilon, the proof works. In a formal proof, you say, for any epsilon greater than 0, let n be the smallest integer that's greater than 17 over epsilon, and then you proceed to do the proof, leaving your reader wondering, how on earth did she figure that you needed to use 17 over epsilon? That's what I mean by throwing out your scratch work. And if your goal is to instruct your audience, it might be that something that's a bit longer than a true formal proof is appropriate. Now let me present some theorems about limits. We can prove all of these from the definition, and most of them will in fact be proved in class. First one, if S sub n converges to S, and I multiply everything in the sequence by some real number k, the sequence k times S sub n converges to k times S. Next, equally obvious but actually great fun to prove, if S sub n converges to S and T sub n converges to T, then the sequence whose general element is S sub n plus T sub n converges to S plus T. And those of you who've been teaching calculus are probably aware that you need these results in order to prove the rules that your students learn about derivatives, like the derivative of the sum of two functions is the sum of their derivatives. Next theorem, if a sequence converges, it's bounded. That is, if S sub n converges to S, there exists some real number m. Usually one chooses an integer for this, but that's not necessary, such that every element of the sequence has the property that its absolute value is less than m. How can a sequence fail to be bounded? It can fail to be bounded if there are terms that are positive and arbitrarily large or negative and arbitrarily small. But such a sequence doesn't have any chance of converging to anything. Next, if S sub n converges to S and T sub n converges to T, the sequence of products, S sub n times T sub n, converges to S times T. We'll need this eventually to prove the product rule for differentiation. Another in the same family, and this one's a little bit trickier. If S sub n is a sequence that converges to 0, and you multiply each term by the corresponding element of the sequence T sub n, then the limit of S sub n times T sub n is equal to 0. But there's a catch. T sub n has to be bounded. Why? Well, I can give you a simple example. Suppose that S sub n is the sequence 1, 1/2, 1/3, 1/4, 1/5. That certainly converges to 0. Let's pick an unbounded sequence T sub n, 1, 4, 9, 16, and so on. If I multiply the terms together, I get 1, 2, 3, 4, and so on, which certainly doesn't converge to 0. And it's because of that sort of counterexample that we need to impose this boundedness restriction on T sub n. Finally, What about a sequence of reciprocals? Well, here we have to be very careful not to divide by 0. If S sub n is different from 0 for all n, so that we can take the reciprocal of any element, and furthermore, the limit of the sequence is different from 0, it's entirely possible to have a sequence like 1, a half, a third, a fourth, a fifth that converges to 0 even though no element of the sequence is 0. Then the infimum of the absolute value of the sequence is positive. That is, there is some non-zero number that's small enough that every element of the sequence is greater in absolute value than that. And if all those conditions are satisfied, we can prove that 1 over S sub n is a sequence that converges, and it converges to 1 over S. Once we have these limit theorems, they will generally provide the best way of figuring out the limit of a sequence. And there are numerous examples in the textbook about how you can use these limit theorems to figure out limits in cases where doing a brute force formal proof would be tedious and unpleasant. Let me conclude by saying a bit about infinity. First, let's consider a bounded subset of the real numbers. And in order to avoid it being trivial, let's make sure it's a bounded non-empty subset. This always has a supremum and an infimum. Both of these are real numbers. The supremum is the smallest real number that's greater than anything in the sequence. The infimum is the largest real number that is smaller than anything in the sequence. But what if the subset is unbounded? Well, there are two ways a sequence can be unbounded. It can fail to be bounded above, or it can fail to be bounded below. Indeed, it can fail in both ways. If S has no upper bound, then we say the supremum of S is plus infinity. If it has no lower bound, we say that the infimum is minus infinity. That means that every subset of the real numbers has a supremum or an infimum, but it's not always a real number. Plus and minus infinity are not real numbers because they don't satisfy the field axioms. You get into serious trouble with things like 0 times infinity. When we're specifying limits, the infinity symbol has a precise meaning. When I say the sequence S sub n diverges to plus infinity, what I mean is that the terms in the sequence become arbitrarily large. No matter how large a positive number you choose, you might choose 1,000, I can find a capital N such that once you go beyond that point in the sequence, I choose n equals 2,000, and every element of the sequence beyond the 2,000th element would be greater than your 1,000. Notice that in order for a sequence to diverge to infinity, the elements of the sequence have to become and remain greater than any positive number. And in exactly the same way, we say that a sequence diverges to minus infinity if no matter how negative a number you give me, I can find a place in the sequence beyond which all the elements of the sequence are less than your capital N. So now you know about limits, you know about sequences, you know how to use the infinity symbol, and we'll get together in class, prove most of the results that I've mentioned, and do a few interesting examples of calculating limits. Here are some of the theorems we're going to be proving. If you have a sequence that diverges to plus infinity, and you have a second sequence t with a positive limit, then the product of the two sequences also diverges to plus infinity. Notice the restriction that t sub n has to have a limit that's greater than 0. If the limit is 0, the limit of the product could end up being finite. If you have a sequence of positive real numbers, then it diverges to plus infinity if and only if the limit of the sequence of reciprocals is 0. If you have a sequence that diverges to plus infinity, limit of Sn is plus infinity, and you add on another sequence, then the limit of the sequence S sub n plus T sub n will also be plus infinity, except we have to impose some requirements on S sub n. If S sub n becomes extremely negative, this may not be true, and here are 3 more or less equivalent properties. If T sub n approaches a limit other than minus infinity, this is true. It doesn't actually have to approach a limit. All that's really required is that T sub n is bounded. And in fact, we only have to worry about adding on very negative numbers, so it only has to be bounded below. So this is the minimum criterion we have to satisfy. The infimum of T sub n has to be some number greater than minus infinity. There has to be some finite negative number with the property that everything in the sequence is greater than that. Okay, we're done for today. See you in class tomorrow.